This is lecture 30. So last time we talked about how Xenu keeps track of the uh, free regions in main memory using a data structure called free list. So there was this free list data structure, and the item to note was the optimization that the free list itself, so this kernel data structure, is embedded into the free blocks, into free memory blocks. So it's not put into a separate kernel region, but it itself is embedded into the free area, and we saw that this is indeed possible to do, and it's a nice optimization. We also talked about the fact that heap under this method of using a free list is just nothing but searching through the linked list of free memory blocks and looking for an element that is big enough to meet the request of getMem, say, and heap means first fit. That's what leads to heap. Hence, the heap grows from low memory. This is low memory and this is high memory, laid out, of course, horizontally. And in this case, using the same free list, heap means first fit. Conversely, stack areas, so stack comes into play when we create a new process. So we spawn a new process, and one of the arguments specifies the stack size, the total stack size that's allocated to a process. And we drew the layout like so. So this is done on demand at runtime. So this is, of course, here it's done statically by the compiler. This is done at runtime dynamically. Dynamically. Now, when we are calling create to create a new process, we need to allocate a new stack, and we do it from the same free list as heap. The only difference is that it follows a last fit policy. So it's a unified method. The only difference that distinguishes heap memory for malloc versus stack memory for forking a process is first fit versus last fit. Also from this picture, we can conclude, that is, we can derive certain implications. So for example, this stack was allocated to the uh, first process that was created. Well, of course, we are here overlooking the fact that the null process is not created using create. Everything is statically, everything is handcrafted. But let's overlook that issue here for the moment. And then here is the stack that's created, that's allocated using the last fit policy for the second process, third process. But suppose that this guy, suppose process P2, now terminates. So when P2 terminates, its stack gets freed up. So now you can go back to the code that we examined earlier. We talked about what happens when a process terminates, and you looked into the system called kill. And when you follow this guy further, you will find that there's something that is going to free up this stack. Well, freeing up means returning this area here that was allocated to P2, which is now terminating. It's being removed from the process table and returning it back to Xenu's free list. So this now becomes free. So this now is free. That means that when some other process is created, suppose we are now calling create after this guy has been uh, terminated, and we are calling create, and we are creating a new process, suppose process P6. You might think P6's stack is somewhere here. It is after the stack of P5, and that might very well happen. But depending upon the timing of when P6 is created and when processes that were created prior terminate, it can very well be that P6's stack is actually allocated right here. That is, this becomes P6's stack. And of course, depending upon what this thing looks like, the entire region may not be the area that's filled up by P6's stack, because of the fact that the argument that's provided for create to create P6 stack may be smaller than the argument that was provided for P2's stack. So here again, we can have this fragmentation develop, that is, holes can develop in this layout. And this is relevant in the sense that in Lab 4, you are looking at ways of making processes behave in a manner that they were not designed to behave. So this is from an adversarial viewpoint, aka a hacker that compromises a system. And one of the simplest way for a hacker to compromise a system is not what you are doing in the lab, which is much more surgical, it's much more sophisticated. Another way for a hacker to try to create havoc is to just destroy this stack area. So just overwrite into this stack area. So there's a return address here, but the attacker doesn't know what is the address at which the return address of some function is located. So all that the hacker does, the hacker has some guess that the return address lies between here and here. In which case, the hacker is going to override all of these locations with a new return address that makes it jump to its malware code. And in so doing, it depends again in how the stacks are laid out, where, for example, if stacks are in this formation and these are, say, the threads of the same heavyweight process, then you could just overflow, if you know this stack, into this stack and just keep writing, and thereby overwriting or destroying the previous information with information that you want to insert. And so to detect whether such destructive actions are employed, so these are non-surgical actions. What you are doing is a sophisticated kind. So this is the more coarse, crude way of attacking, which is quite common because attackers have only partial knowledge about the victim system that they're trying to compromise. So if it turns out that they are doing something rough like so, then it's possible that in so doing, they end up overwriting this area, including the first part of a process stack. And now if you go back to Lab 3, where you were asked to look closely into the layout of a stack, you would have noticed that the beginning of the stack is populated by a so-called magic number. So it's a bit pattern, typically denoted by magic something, magic bytes, magic word, magic number, and this is a specific bit pattern. And one of its uses is if an attacker is employing such a crude method of trying to compromise the victim, in most cases trying to override the return address here with the address of the attacker's function, so that when the victim, which is engaged in nested function calls, is going to then use this address to return to a previous function, it actually jumps to the malware that the attacker has put somewhere. But because the attacker is crude, the attacker may be overwriting this magic number with the return address as well. So this magic number is now distorted, it's now corrupted, it's changed. So when it comes to a function ABC, suppose this is the app code of some app, and this app code ABC, this function ABC calls DEF. So this is the caller, this is the callee. And DEF at the end does a return. So there's a return, and we know that this translates to red in x86. So when this thing translates to red in x86, it means it uses a return address that's remembered in the stack to jump back to this guy. That would be the normal operation. This red causes a jump to the next instruction after the call of def, inside the caller. But suppose the attacker has overwritten the address so that it would jump not to ABC, but some malware XYZ. This is the attacker's code. So this is the attacker's code, and the attacker, by overwriting this return address, wants to force this return to jump to the attacker's code, to the beginning of the attacker function XYZ. So this is malware. This is normal app code. But what you can then here do is, in software, you can check before executing red. So before you execute red, you can insert code. So this is again epilogue code. So we talked about epilogue code in the context of process synchronization, but this is a very common software engineering technique. Epilogue code at the end, prologue code at the beginning, to insert things that are useful to do. So in this case, a compiler, if so instructed or by default, could insert code just before executing red. And what would this code do? It would go to the beginning of the stack and check, has this magic number been changed? Because this magic number is a specific pattern. So this epilogue code can certainly check, is this bit pattern still what it should be? If it is not, then it knows, oh, something has happened. And it would not jump back, it would terminate the process, which would limit the damage that an attacker might be able to do. Furthermore, this is in the case of the whole stack being compromised. Another way that, and this is the more common way that an attacker would try to compromise this, here is the stack of a process. This is the entire stack, and it's made a bunch of nested function calls. Maybe this is for main calls ABC, and ABC calls DEF. And we know from cdecl that the return address that DEF should jump to is recorded right here. And the attacker would then try to override this this return address that would jump back to ABC where it left off with a different address. So this would be corrupted so that it jumps to, so that it contains the address, the beginning address of this malware XYZ. But again, if the attacker is not surgical, doesn't know exactly where this return address is located, then it might just override this guy, this guy, this guy, a bunch of words, a region is overwritten with the return address, which jumps to this malware XYZ just because the attacker does not know the exact information and so employs this crude attack. So it doesn't only override this guy, it has this collateral damage. Well, in the same way, when DEF, so this is the code of DEF, like we said earlier, here's our DEF code, and the last thing is return, of course, in assembly language. So before return, the compiler could insert, so here, it could insert epilogue code, which checks, not for this value, but it checks a value just below, somewhere here. Let me highlight that in green. So here's a specific magic number that's been inserted. So here's a magic number, a magic bit pattern, a magic word, just below this return address typically. And when you do so, it's typically called a canary, the bird, canary. I hope I'm spelling it right, canary. And if the attacker were to employ such a coarse method of modifying this return address, which overrides the neighboring words with the return address, it would of course change this special bit pattern, which should be something. And the epilogue code can have an if statement somewhere that compares this canary, which should be a specific pattern again, specific bit pattern, to check that it's still the specific bit pattern. But if the attacker overrode this guy with the return address of its malware, this will have changed. So it notices, oh, my canary has actually changed. My canary bit pattern here has changed. And that would tell that something is not right, and it would cause the process to be terminated so that you don't run this malware function, which might do damage. So the aim here is to not let the attacker's true malware function execute, which then can compromise the system further. And it's called a canary, as you can imagine, because I guess maybe still in part, but now we have technology. But in the past, when coal miners were digging coal, which is a very dangerous activity, and it can release gases that then can harm humans, they brought along this bird, and birds typically have a much more sensitive respiratory system, and this guy is apparently quite sensitive, so that if dangerous gases are released by digging for coal, then these guys would faint and die first. That gives the coal miners some time, that is a heads up time, to then escape, hopefully, before the gases then impact humans. So this is the notion of canary. And so in a similar way, we implant these canaries just before this return address, so that if a coarse attacker does compromise the system, then because this canary has died, that is its bit pattern, is now not the bit pattern that it should be, we can then take action appropriately by terminating this process before it jumps to the true malware code. Of course, all of this entails overhead, and if you're doing this thing surgically, this magic word, this canary, has no use. So these are all partial methods to try to mitigate uh, an attacker's effort, but these are all imperfect in that sense. All right, so with that in mind, now let's go further down here. So this is the issue of protecting against Stack Overflow and some of the background. Now back to Xeno in terms of memory allocation granularity. This means when we ask for bytes in getmem, then is it allowed to ask for 1 byte or for 2 bytes, for 3 bytes? Is there some minimum unit that we can request? And the answer in Xeno is yes. In Xeno, the minimum size that can be asked for when requesting memory is a block of 8 bytes. So it's in units of blocks of 8 bytes. So even if you ask for 6 bytes, you get back 8 bytes. 2 bytes are wasted, obviously, here. And that wastage is not too big because it's only in total 8 that you're giving back to begin with. And today's memories are quite large, but there is some wastage going on, certainly. In terms of percentage, it's of course a large number because if you are giving 8 bytes when you only need 6 bytes, then this extra 2 bytes is a third of what you're requesting. So that's going to be about 33%. So that's a lot in terms of percentage. But keep in mind that you don't want to just blindly use percentages and then say, oh, this is big or small. You have to keep in mind the context that in this case, the biggest block size is 8 bytes. So there's an absolute number that's attached to that. So don't fall into the trap of just believing absolutes or just believing these percentages, which are of course relative. They all serve their purpose, but they have to be used appropriately to be meaningful. Just using percentages all the time, just using absolute numbers all the time, that's going to lead to typically bad conclusions. So keep always in mind you have to have both to accurately convey what's going on. In this case, the absolute is 8 bytes. That's the multiple by which. And so if you're asking for 1 megabyte, suppose you are going to ask for 1 million and 2 bytes, and suppose that you get back 1 million and 8 bytes. Clearly, for the last block, you are only needing this much, but you're getting more back. But it's still within the purview that is within the limit of 8 bytes. So it's not a big deal. In Xeno, this rounding function is going to round up to 8 because that's the unit by which we are using it. And in Xeno, the free list is maintained by this struct called memblock. It has 2 fields, a next pointer because it's a linked list as we said, and then the length. So in Xeno, we are not indicating in this free list the beginning address of this block, the end address. It's the beginning address of this block and the size. So m length is the size. So we are using this representation. And how big is each element? This is a pointer in our architecture. It's 4 bytes because it's a 32-bit architecture. This is uint32, so it's unsigned integer. So in our architecture, it's again 4 bytes. So each linked list element takes up 8 bytes of memory. In the earlier example that I used to describe free list, I used, I think, a number like 30 bytes. In Xenu, the actual number is 8 bytes. So 8 bytes need to be embedded. But that of course makes sense because in Xenu, the minimum block size, and everything is in units of that, is 8 bytes. So it's just enough to fit in this kernel data structure for one linked list elements, which is comprised of 2 fields, each 4 bytes, hence in total 8 bytes. This entire free list is pointed to by the head list, but the head list is not just an address that points to the beginning of this linked list element. This variable memlist is not a pointer to memblock, it is itself memblock. And the reason being, you could certainly make it point to the beginning, but we also want to remember in the header that points to the entire free list, we also want to here store how much memory in total is available. So it's this first memory block, its size, maybe this is 20 megabytes big, this is 50 megabytes big, and this is 15 megabytes big. Then we want to remember that the total free memory, not the contiguous memory, but the total free memory is 20 plus 50 plus 15, so that would be 85 megabytes in total of free memory, just for bookkeeping purposes. And this can be remembered inside the length field of the header element. So the header itself is of the same struct. It has a next pointer which points to this guy and a length field which is going to say 85 megabytes, which is the total sum of all the free elements here inside the free list. So one such twist. And a couple of pointers to keep track of where the heaps are located. So let's go down further. And why is it 8 bytes? Well, it's a reasonable number. It can be 16, it can be 32, it can be any other number, and all of them can be made to work. In Xenu, we are using 8 bytes for that. This is the same as before, and here's a nice illustration of the free list in Xenu. So here, we are seeing that there are, one free region, that's the first free region, second free region, third free region, fourth free region, and fifth free region. So there are 5 of them. And this is the header guy. This is just purely bookkeeping for bookkeeping's sake. So this guy points to the first free region, that's the next pointer, and then the other field indicates what the total free space is. And this number better be equal to this guy's free region. So this says this is of size 16. This says this is of size 24, 32, some unit, for example, megabytes, 16 megabytes, 40 megabytes. Because this is the actual free memory in RAM. The first 8 bytes, these guys are embedded. That is, we said the optimization is to embed the kernel data structure of the free list, which in Xenu now is comprised of 8 bytes. They are all embedded inside the free memory itself. So we have already discussed that, and this is how it looks like with the specific values used in Xenu. And it has 2 fields, the next field obviously, and then the size field, the length field. And the length field says this is the total free space. Suppose it's in megabytes, for example. And the total, 16 plus 24 plus 32 plus 16 plus 40, that's the total free space. and that should be equal to 128. So this is why making this not to be a pointer to the struct, but itself the same struct is useful, because you get this extra field where you can store the sum of all the lengths of all the sizes of the free elements. So now let's go further. So we talked about first fit, last fit, and free list. Of course, the end of the guy has to have a null pointer since it's the end. And then we have the system calls that return when we call getMem, the first address, that is the beginning address of the memory that's been allocated, assuming that the free list is big enough or has an element that's big enough to satisfy this need. But the first thing that we do in getMem is we are going to round it up so that it becomes in units of 8 bytes. And then all that we're doing is going through this linked list. So this is just data structure 101, going through the linked list and checking for in getMem for the first fit, for the first element that's big enough to meet the request. Either we are lucky, the bytes that we need after rounding up to be a multiple of 8 bytes is just enough. That's really great. Or hence we return because we've done a first fit. Or it's bigger. That's fine too. We return again. Else it means it's not big enough. So we skip to the next element by jumping the pointer. That's it. But then why are these if-else comparisons? Because we need to deal with the specifics of this data structure, such as suppose that here is an example of a free list. So these are the three. Here is our head guy, and I'm not going to throw this guy in detail, but these are the three free regions. First region, second region, and third region. And suppose this guy is of length, of total size, 1 megabyte. This guy is 3 megabytes. And this guy is, say, 5 megabytes. And the user says getMem 3 megabytes. Just the same size as this. And we are here going to not worry about being multiples of 8. This is just to illustrate the concept. So in this case, purely by happenstance, what's being requested is exactly of the size of this guy. This guy will not match, so we will go through the list from the beginning. This guy, of course, this guy is too large for that, hence it's this guy, so we jump to the next element, and now this actually is an exact match as this. This is the equal condition. When it's an exact match, then what we have is that we are going to return this address, which is of course the next address that's pointed to by A to B by getMem. So that's clear. What should be this guy's next address? It would of course be here. This entire thing is now gone because it's been allocated. And that's what creates a new list with one less element. Conversely, suppose that we have a linked list like so. Actually, for the freeing case, let me not use the linked list, but let me just draw it as a picture in main memory itself. I think that's even clearer. That's hopefully clearer. So let's see. So suppose here is our main memory, and this is extremely simplified to show why we need all these conditions. And suppose that this memory is free and this memory is free, but the rest is all occupied. And now we call free mem and we provide this address, this guy. So this is all occupied and the size being exactly this much. Well, after this free mem goes through, in this particular case, this free list was comprised of two elements, that's excluding the header, this guy and this guy. But after this free mem goes through, the number of elements now shrinks from two free guys to one guy. And that one guy is this entire region. This is now a large contiguous region that's now made free. So these are again borderline conditions. So these are border conditions. So when we are going to allocate memory and we are now going to free memory, we need to make sure that we check for these conditions where what we are allocating and what we are freeing is exactly the size of what we have available in the free list or its complement, which is the memory that's being occupied already, that's now being freed, that it actually fills in exactly this gap between. So these are all obvious things, but I'm just trying to indicate without us going through this entire code here line by line, as it's only data structures 101, why these conditions are needed. So the basic idea of free list we discussed already. When we are implementing this inside Zeno using code itself, it's fundamentally just a linked list traversal, looking for the first guy that's big enough. That's the uh, first match policy stack. It's the last match, but we need to be mindful that we are dealing with all these corner cases, these border cases, so that the code works correctly. That's what here is worth noting. Otherwise, it's just simple linked list traversal. So with that in mind, so we can you can go over this in detail uh, in terms of manipulating this. That's not something that we are going to do inside the lab. So hence, it's just for your reference. So here are just some more words about splitting, about these things, deallocating. Here, coalescing. The example that I gave just earlier is about coalescing blocks. And here is the case of free mem. And again, it has to have this if-else conditions to make sure that we manage all of these cases properly. That's it. So get stack is going to be like get map, but it's going to be last match. So just because you find in your linked list traversal that you find an element that's big enough, you're not going to return immediately. You're going to go through the list until you hit the end of the list. Each time when you find a block that's big enough, you're going to then remember it. And then after you've hit the end of the list, so here, if it is big or equal, then you're going to remember the last guy that meets, but you're going to still go through. And then if fit is null, it means there's no element that's big enough. Then you're going to say, I couldn't find it. So obviously, and else you found it. And then you need to again worry about corner cases and update the data structures accordingly. That's it. And in terms of free stack, it can be just coded in terms of free mem, because keep in mind the stack, the difference in stack is a stack is viewed as growing this direction. So this is the beginning of the stack, and this is the top of the stack if this is being occupied. But in terms of the free memory, what you get back is the beginning address of this free block. Of course, for stacks, you don't care about the beginning address, you care about the end address. And so slide conversion needs to be made to make sure that we are still using it from the free list in Xenu, where memory is organized low to high. But when we are allocating stacks or we are freeing stacks, then we must be mindful that for stacks, we are maintaining references with the view of things growing downwards. And so these two different views must be, of course, reconciled, because at the end of the day, everything is truly from low to high, and a stack which goes in the opposite direction is just an abstraction that we employ for our purposes. So here there's no need to code this free stack from scratch. This way of defining a macro will suffice. So now we jump to what is advanced memory management, which means that it's about hardware-based memory management. That is, it uses hardware support. But before we do that, we need to talk about a super important topic under basic memory management, which is fragmentation. And it's a very important concern. It is kind of like deadlock being a very important concern under process synchronization. But with deadlocks, we talked about isolation protection, allowing us to say it's not the kernel's responsibility to detect and to deal with deadlocks, because its damage is limited to the process, that is, to the processes of an app that engage in deadlocks, but not so for this thing called fragmentation. So what is fragmentation? So let's here go to So we talked about already one type of fragmentation. So in Xenu, the minimum block size is in units of 8 bytes. So if I ask for getMem, I ask for 2 bytes, I will get back 8 bytes. So 6 bytes is being wasted, and that's called internal fragmentation. It's not nothing, it still is wastage, but it's typically not considered the critical issue in today's environment. There's another type of fragmentation called external fragmentation. And that's the one slide that we skipped over in our common PDF slides talks about in one slide, but it's much more involved than that. And it will be also one reason that motivates or that benefits from advanced memory management or virtual memory management. So what is this external fragmentation? It can be easily illustrated by an example. So suppose here is our main memory. And we are using from here to here. So this is the beginning and this is the end, or start or end, however you want to demark. So this is beginning, so this would be the end. And this region is subject to now basic memory management in Xenu using getmem, freemem, etc., as we just discussed. And now suppose what we have is that this memory is free. Suppose this memory is free, this memory is free, and this memory is free. And suppose this memory is of size 60 megabytes, this memory is of size 50 megabytes, and this memory is of size, say, 20 megabytes. So this is free memory. So the total free memory, and I'm not showing here the free list, just where they are located, is going to be 50 plus 20 plus 60 megabytes. So that's going to be 130 megabytes. So that's the total free memory. And now suppose a process runs and it calls getmem. So it calls getmem and it requests, say, 100 megabytes. Obviously, the total space that we have available that's free is 130. And that's certainly bigger than what's being requested. But the problem is, this memory is not contiguous. There's this block which is of size 50, this block of size 20, this block of size 60, but it's not contiguous. It's splintered. It's fragmented. So although the total free memory is big enough to satisfy this request, the largest contiguous memory is only 60 bytes, which is clearly smaller than the requested size 100. So the fact that the total is enough, but there's no contiguous memory that's big enough, that is what we refer to as external fragmentation. And this is a very severe problem. So when you have an operating system that is now running a bunch of processes that come and go, that terminate, that allocate dynamic memory, free memory, etc., then eventually, after a while, this memory here becomes splintered, like this one-dimensional Swiss cheese with all these holes, and it becomes splintered or it becomes fragmented. And the issue that we care about is not so much internal fragmentation, that we are wasting some bytes, which is not a huge deal because it typically is a problem of only the last block. So it's all in units of 8 bytes, 8 bytes, 8 bytes, 8 bytes. So it's only the last 8 byte that may not just fit what you need to accomplish. So it's not a big deal. But what is a big deal is because it gets so fragmented, the total free space may be still fairly large. But when a getmem system call is made to request some amount of contiguous memory, although this one is sufficiently large, there's no contiguous block of the requested size. That's the problem of external fragmentation. And it causes apps that would be able to get their memory and run to not be able to run because this guy will return an error. It's the same for Linux Windows when we are using user libraries like malloc that internally make system calls to request memory. It would then return an error saying, I can't do it because there's not enough contiguous memory in this particular case. And this is severe enough that this has to be addressed. And the solution to this problem starts with a software solution, but so there's a software technique that we can use to address external fragmentation, but the software technique would be too slow and cumbersome. So hence, we need hardware support to make it fast, to make it efficient. But what is the software technique that we use to address this problem? So what is this? So the problem is, the issue is external fragmentation, and we need to find a solution to that. And one solution that we use on disks, because the same goes for this. You put files, you delete files, disks become fragmented, as you may know. So what can we do? What can we do on disk? We are not discussing file systems and disks, so I'll talk about what the idea on the disk would be. So if this would be our main memory, and this is free space, this is free space, and this is free space. So here I used, in the previous example, 50 megabytes, 20, and 60. So I leave out megabytes, so 60, 20. And we get getmem for 100, and the total is enough, but of course there's no contiguous skylarch. So the technique that one might use for disk would be defragmentation. Defragmentation, which means that we move around this free memory. For example, here's the 50. We move this 20 from here down here. So here. So now this is the 20. And then the 60 here, we move from here down here. That's where 60 is. So now comes 60. And as a result of defragmenting, that is moving things around, we're able to create this contiguous space of 110 megabytes. So now it's contiguous. And now if getmem comes along and asks for 100, well, we have here 130, that's plenty, and we're able to satisfy this. The problem with this are several-fold. One is we have to copy. Copy cost is linear, as we said. One of the slowest things that you can do in a system is copying. So you want to avoid copying to the extent that it's possible, because it involves linear cost, as we mentioned. And in systems, certainly in operating systems, linear costs are to be avoided at all costs to the extent that it's avoidable. So copying around things, which sounds easy and nice, is just overhead ridden, and we don't want to do it. That's one issue. Here there's another issue, which is to copy, say, this guy from here to here is tantamount to saying that this area, which is occupied, so it's being used. By definition, only this area, this area, this area is free. Which means that this area to which this free area is being moved to, hence freeing up, now needs to be, of course, reverse copied. So therefore, we would need to copy this content from here to here, because this guy has to go somewhere. Now, this may be okay for files and such, but imagine this area has already been returned Here I'm using Xeno as our example. It has been returned by getmem with a pointer. And a process P5 called getmem, and this getmem returned a pointer to the beginning of this address. And P5 is still running, and it uses this live pointers to read-write to this memory here. But now the kernel has moved this content from here to here. So the pointers that were returned to P5 earlier are not correct anymore. They have become stale. They are incorrect in this sense. So the fact that when you move things around, and these are occupied areas, which means that addresses, pointers are being used by running programs, this must be properly resolved. How can they be resolved? They would have to be resolved by making sure that the pointers are renamed. So if this was an address, suppose 1 million, and this address now is moved to here, which is suppose 2 million, then we need to make sure that this address that P5 is continuing to use, because we are not rewriting P5's code, now is viewed as address 2 million. So there has to be a mapping that's performed from 1 million to 2 million in some way. Otherwise, this defragmentation wouldn't work to begin with. But this remapping idea to make this tail pointer that would otherwise not be valid anymore, because this now is free. The content here has been moved here, but this P5 guy still thinks it's down here. So you would be corrupting this process. That's of course not good. But making P5 use this old address, but then remapping this to a new address, this technique is called in computer science indirection. When you programmed x86 in AT&T assembly, then for some of the addresses, we applied indirection by putting a parenthesis there. When you're using star in front of some variable a in C, and it says it's a pointer to int, it's called indirection. If we put 2 stars, it means it's a double indirection, triple indirection, etc., etc., etc. So we are not going to be doing any copying because of the overhead, but we are going to borrow this idea of indirection to address this problem of external fragmentation, not using this defragmentation approach, for example, used on disks where we store files. Instead, we are going to use only part of the technique called indirection plus special hardware support for speed to resolve this issue of external fragmentation. So we are going to introduce this hardware support. And once we introduce this hardware support, we are then going to go full-fledged and create what is called a virtual memory management system. So we'll discuss this stuff in detail in the next lecture.